Okay. I need to check and make sure that my YouTube stream is working, I think. I can't tell if the quality is super bad because it's warning me that the quality is super bad, but if you guys have input on how god-awful the quality is, or if it's okay, let me know. Because it's got a warning about lower than recommended bitrate. Also, I have prepped a lesson plan, but I actually haven't prepped it using the computer drawing software yet. So we're gonna see how well it plays out. If I am really bad at drawing on the computer drawing software live, then maybe I'll have to pre-prep slides or something later on. Enbu says quality looks okay, good. Awesome. So yeah, today we're gonna talk about cars. It's gonna be super cool. I really like this subject, because we're gonna be talking about the systems of wheels on your cars and how they sort of have to be really well coordinated with each other. It's not just, you take 4 wheels and you make them spin and the car moves, because it's actually quite complex in how they have to be orchestrated together. So I think it's super cool, and I'm really looking forward to sharing it with you guys. Dang. Background music goes hard. It's not too loud, is it? What up, Ash? Hope you're having a good day. Hope it's a swell Tuesday for y'all. We'll probably get started in just a minute. Just checking some last stuff to make sure we're all good to go. Making sure my drawing tablet is working properly. Cool, cool. What kind of tea are you having, Ash? And I'm super glad that the audio is good, Penbu. Thanks a lot for the support the other day. I really appreciated the raid. And I probably should have thanked you during the stream, but I was just a little caught up in the moment. I have alerts set up now though, so I'll be able to stay on top of it a little bit better. Alright. Let's go. Oh, great. That sounds fancy. I'm not really a tea drinker, but I know that's like a very refined thing to drink. I personally just like sweet drinks, and tea has never really been, at least like normal tea has never been like, never done it for me. Alright, let's get going. Okay. Quick check that you guys can see Krita. You can see me drawing. And I am a little bit in the way, so we'll go here. Thanks, Ash. I worked really hard on it. So I'm super glad to hear that you like it. Alright, let's get started. Ooh. To find a good place for my mouse. And... Alright, chat, so let's talk about cars. Today, I want to talk about the ways that your car has to sort of orchestrate all its wheels in conjunction with each other in order to drive properly, because there's actually a lot that goes into it. So, just for reference, before we start, I'm gonna make all of my examples about a car with rear-wheel drive. But everything that I'm going to talk about is applicable to all cars, right? So rear-wheel drive is like you have your engine in the front, right? And it's going to send its power all the way to the back to an axle that has both the rear wheels. And I'm just using this because I think it's an easier example for some of the things I want to talk about. But like I said, everything I'm going to talk about today applies to all of your cars. It applies to them regardless of what form of drive they have. Okay, cool, so let's go. Alright, to start with, we're going to start with some basics. And it's going to start really boring, but I promise you, it will get more and more interesting, and at the end we'll be talking about some really cool stuff. Okay, so I want you to imagine a wheel of some radius that gives it circumference c, which I know this sounds a lot like it's gonna turn into math, but I'm gonna really avoid doing math. So it's just this beginning part. So obviously with circumference c, if it goes all the way around is the length c. When you rotate this wheel once and you make one rotation, it's gonna cover c distance, right? Pretty simple stuff, but just in case anyone's not necessarily up with the program, this is how wheels work, assuming they don't spin. So if we have one wheel that spins once with circumference c, it's going to cover c distance. And now what I want you to do is I want you to imagine a second wheel, also circumference c, that is linked with the first one, so that when the first one spins, so does the second. If the first one does one rotation, the second one does one rotation. And so, of course, that means when the first one rotates once, and the second one rotates once, the second one also covers distance c, right? And it sounds stupid because I'm just repeating myself, but it's gonna make sense when I'm talking about this in a little bit. Okay, so if you imagine a dumbbell, right? And you go to the gym and you have a dumbbell, which is basically what these two wheels are. It's two wheels mounted on the same axle, so they spin together. If you roll a dumbbell across the gym floor, you'll notice that your dumbbell always rolls straight. And it's because of what we just talked about. I drew this probably a little too small, or a little too large. Because of what we just talked about, where the whole dumbbell makes sure that both sides spin at the same rate. So one rotation on the left is one rotation on the right. And that means if the left side covers C, the right side also has to cover C. It means it has to go straight. It can't turn because in order for it to turn, one side has to go a longer distance than the other, right? So for it to turn, this right side goes a tiny distance and this left side goes a long distance. So they're mismatched. That is why your dumbbell's gonna roll straight. Alright? No quiz, Ash. No quiz. You can just, if you just want to zone out, you can zone out. I am just here to yap about engineering because I think it's cool. Alright. So we have established that, you know, with this situation where we have two wheels linked like this, they can only roll straight. The only way that it would ever turn is if one of them is slipping. Of course, when you're driving your car, you don't want your tires slipping. So cars, we definitely want to avoid any situation of slipping. So slipping is bad, does a tremendous amount of damage to your tires, and it can do a lot of damage to your drivetrain too. But anyway, so with the dumbbell model, we can't turn. All right, so how do we make a car able to turn, right? In order to make it turn, we need to deal with this problem where one wheel covers more distance than the other. So how do we deal with that? There's a couple of ideas, right? I mean, the first possible option is what we do is we can make one wheel bigger than the other. And so with our larger wheel, of course, we're going to cover a longer distance with one rotation. And with our smaller wheel, we're going to cover a shorter distance. And that's going to enable us to have that turning path with the long wheel, the larger wheel going the long distance, and the smaller wheel going a short distance. And so it sounds really silly, right? Because you obviously don't see cars with like one wheel bigger than the other. Why do you have dumbbells on your desk, guy? Alright, but anyway. So if we think of this sort of same model with the dumbbells, but we instead place them where one wheel is bigger than the other, right? I like to think of it as sort of an ice cream cone, right? With one small and one big. And what happens, your ice cream cone looks like this. There's like a center turning point, and your smaller section traces out a tiny circle, and your larger section traces out a bigger circle. Right? And like I said, you never see a car like this. Of course, you don't see cars with these ice cream cone wheels, but it's sort of an interesting idea, and there's some application to this idea later on. I just want you to remember this sort of model, the sort of ice cream cone wheel model. So yeah. And who knows, maybe in the future we'll have it. But that'll come, like I said, we'll come sort of back to this model later in the talk. And it's later on down the road when we talk about trains. We'll also sort of talk about this too. Just keep this idea in the back of your head. So anyway, we can't have cars with one wheel bigger than the other unless we wanted a car that only turned. So that's not how we deal with it in cars. So how do we deal with it on cars? On cars, what we do is we use this device called a differential, right? So when you're talking about a rear-wheel drive car, we had an engine, sent power backwards to the rear axle, that went to both wheels. So what the differential does is the box that goes here, where that main drive shaft connects with the rear axle. And what it does is it routes different amounts of energy to each wheel. So disclaimer, I said energy. Energy is a physics term with a very physical definition. What I'm talking about is definitely not matching the physical definition of energy, but I think that's the most natural word for me to use here. So what the differential does, like I said, is it routes energy to the different wheels at different amounts. And how it routes the energy is it sends more energy to the side that has less resistance. So if you think of the turning idea, right? If we're turning to the right, this wheel goes further, this wheel wants to go further, and this wheel wants to go shorter. So in that sense, since this wheel on the right wants to go shorter, it has more resistance. And the wheel on the left has less resistance. So because it has less resistance, we end up with a lot of energy getting routed from the differential to the left wheel, and we end up with just a tiny bit of energy getting routed from the differential to the right wheel. Like I said, energy is not necessarily the most precise term, but I think it's a very natural way to think of it. So, like I said, the differential routes the energy towards the side with less resistance, and that helps us to make one tire spin more times than the other. But there's some problems with this. So if you've ever gotten your car stuck, right? If you've gotten your car stuck in mud or on ice, or there's just some weird terrain so one of your wheels doesn't make contact, you'll notice that your car is stuck, and when you hit the gas, only that one wheel spins, right? So we've got our car, our engine that supplies energy back, differential, right? And if, say, this tire does not make good contact, or it does not have traction for some reason, you're going to notice that your car doesn't move because only this tire spins. And that's because since that tire is not getting any traction, it obviously is going to have very little resistance. So basically all the energy coming from the engine is going to route to this tire. And only that one tire is going to spin. So that is why if you have a car made to go off-roading, you might recognize a button that looks like this. And this button locks your differential. So it basically makes your differential stop doing what differentials do, and it makes these tires spin at the same time, right? So however much the right tire spins, the left tire has to spin also when you press this button. So it locks your differential stops doing differential things, and it spins your tires at the same rate. Now, what happens if you lock your differential and then you try and turn? The answer is bad things happen. So, like I said, of course, because your tires are trying to cover the same distance since they're turning the same amount, but they're being forced to cover different distances, they're gonna slip a lot, which is going to shred them, and you're gonna lose a ton of tread really quickly. But also, all that resistance they're facing that they don't normally do, all that stress of forcing them to slip, is actually going straight to your drivetrain too, because your drivetrain is trying to turn them and they're resisting turning the way that they're supposed to. So what that does is that actually does pretty catastrophic damage to your train if you do that for too long. So that's why you don't just press that button all the time, of course. And if you want to know how I know about that, that's me speaking from life experience. There's definitely a time where a younger Breakabelle was driving Papa Bell's car, and she had the differential lock on without knowing it, and Papa Bell was not happy. Papa Bell was not happy with the repair costs. So, sorry Papa Bell, but that was a younger, dumber Breakabelle doing younger, dumber things. And now she knows better. And now I hope you guys also will pay attention, because if there's a little light on in your car that shows the differential lock, you should probably make sure not to do any turns. You should probably just turn it off. You should only really use this if you're in some condition where you're gonna slip, like you're off-roading or whatnot. So yeah, that's differentials. I think differentials are a pretty neat concept. I was really contemplating how to draw them, and I realized that there is like no good way for me to draw them. So I think it's much better for me to just show you a video or a GIF. I should have prepped this beforehand, but now I'm stuck Googling it at the last minute. Where's the one I want? I think this is the one I want. Add window capture. Okay, can you guys see? I have to wait a sec because of the delay. Oh god. Alright, so here's a differential. You can see one wheel on one side and the other wheel on the other side. So what happens when you drive the drivetrain is this middle part spins, and that spins on both. But if you hold one of them, causing more resistance, it spins only the one that isn't getting resistance, right? So it's pretty nifty stuff. And of course this is a very simplified model, but this is basically what's happening inside your car.
In the spaces between the spokes gives steadier, more continuous action, and changing the shape gives firm, constant contact. Now we can make the gears thicker and stronger, and we have differential gears. The edges are cut so that they will fit together more smoothly and...
Okay. Anyway, back to Vita. What did you not think of that way, Penbu? Let's do another sheet. Man, I love engineering, guys. I think this is some super cool stuff. And those of you who might like already be car people probably already know this stuff, but I think it's super cool. Okay, so that was differentials. That was the first part of what I want to talk about. Now we're going to talk about another cool topic. That I think is maybe less likely for people to know about, but I think this is the cooler one, so we're gonna chat about it. So if we go back to our ice cream cone model, right? Go back to the model of turning where one wheel is bigger than the other. There is some insightful information here. Okay, so you'll notice that they turn about this one point, that they are both on the same, that is on the axis of both of them. And because they're on the same axis, it's really easy to say that, oh yeah, it's just, they just happen to be on the same axis as both of them because they share an axis. So any point that's on one will be on the axis of both. But this is actually true of all wheel systems, because if you have a rigid object that is turning about, that is turning really roughly, right? Going from box like that, box like this. In order for that object to not like deform or stretch or strain or get, warped, it has to have a single point that every part of the object turns about. So we're gonna draw, I might have put the point at the wrong spot. But anyway, we're gonna clean this up. But the idea is, the box is turning. We're turning about this point. So that corner is gonna do a circle about the point. This corner is gonna do a circle about the point. This far corner is gonna do a circle about the point. Right, so you can predict the path of the box by drawing these circles about the point that it's turning. Wow, I am a bad artist. Okay? Now, the insightful thing about our ice cream cone model is that what you'll see is the wheels are always have to be perpendicular with the point. So this should be like a little bit intuitive, but if you think of, say, a bike, right? You think of a bike as this long, really slender wheel, right? And the frame, goes around it that way. The bike wheel, this rear wheel on your bike, is clearly only intended to go forwards and backwards. Okay? And that might sound silly and simple, but it's really important because it informs you as to why wheels have to be oriented a certain direction when you're turning. Your bike wheel does not go left and right? It doesn't spin that way. So in order for it to go that way, there has to be slip. And of course, the wheels don't want to do that. We don't like slip, right? So wheels are always trying to go one direction or along one axis. In this case, it's up and down. And that is always going to be perpendicular to the point of turning, because if you're turning about a point, right? That means you have to be going along a path in a circle around that point. And that means to be going in the direction the wheel wants to go, right? Which is up and down. At this point in the circle, we need to be tangential to the circle. Okay? So that means the wheel will always, its axle will always be perpendicular to the center of the circle. All right? Now, this helps inform us of some other cool stuff. So, for example, with the bike, you have the same bike with the rear wheel. Wow, that is oddly shaped. That's the rear wheel, right? Here's the frame, here's the front. And the front wheel, when you turn, say it's angled like that, we can predict where the bike turns about. because the wheels have to be perpendicular to that point. So this bike, when the handle is turned to this angle, is going to turn about this point. Right? This rear wheel is going to go. Ooh. Bad drive. Rear wheel is going to go in a circle. Front wheel is going to go in a circle. And you can predict the exact motion of the bike. So how does this relate to cars? All right. So if you're like me and you think, oh, well, when we turn the car, right, when we want to turn left or right with our car, we need to turn both of the front tires. And the easiest way to do that is to do that with a linkage system, right? So if you're not familiar with a linkage system is basically a bunch of bars. Use some different colors for the ones on the sides. And they're connected by joints that allow them to, like, pivot. Right? So this would be our linkage system. It's parallel to keep the wheels parallel, right? Because your wheels are going to be like this. We have this nice little parallelogram. And then when we turn, if we have this parallelogram geometry, what we end up with is a shape that looks like this. Back to the blue. Right. And then our wheels are now turned. That's what intuitively makes a lot of sense to turn both wheels together, right? You make this parallelogram linkage, and that turns them both at the same time. That's how you make sure that they don't, like, be miscoordinated, right? But you might notice there's an issue. And that issue is what we talked about before, where when the car turns, every point about it needs to turn about the same point, which means there needs to be a point somewhere that is along the same axis of all these wheels. And since these wheels are parallel, there will never be a point, right? These lines will never intersect because they're parallel with each other. So you're never going to find a point. So how do we deal with this? We use what's called, oh my god, running out of space, Ackermann steering geometry, right? So Ackermann steering geometry is this similar, well, it is the same idea with the linkages, except instead of a parallelogram, what we use is a trapezoid, right? We have our trapezoid, and before you pop off like Bell, you're an idiot, our cars aren't like bow-legged, right? They don't have their wheels pointing different directions, which, you know, would be a pretty funny thought. We, of course, correct for this by making these side linkages, instead of just like rectangles, we make them triangles. And wheels are attached like this. All right. So what does this do? How does this change our original issue? Well, with Ackermann steering geometry, when we turn our trapezoid, wrong layer. When we turn our trapezoid, actually end up with some really distorted turning. That comes like this. And we have our black line for the bottom part of the linkage. And we should finish these off by recreating the triangles that adjust, right? So now, when we turn, our right tire, you'll notice, has turned a lot. And our left tire has still turned, but it's turned significantly less. And so now, since it's turned less, if we draw that line for the axis, we have an intersection point. So now we do have a point that the car can turn about. All that's left is to make sure that when we design our car with this geometry, that point is in line with the rear tires. And that way, all 4 tires will always be perpendicular to the one point that the car needs to rotate about, and we can turn the car without slipping. Okay? I think this is super cool. I don't know about you, chat, but this is like a super interesting idea to me. And there's definitely like a lot more math that goes into calculating the exact geometries, but I'm trying not to do that math, and I don't know how to do it, to be honest. This isn't stuff that I've worked on. This is just stuff I know about. But that's Ackerman's steering geometry, and this is maybe in some senses more intuitive than the differentials, but I think this is probably the coolest thing about cars, because I'm a really mechanical person, and just this visualization of changing the linkage shape to make one side turn more than the other, I think it's super cool. And this is my favorite part of what makes cars tick. So yeah, that's Ackerman's steering geometry. Okay. That's all I really had planned to talk about today. But I also did want, because we've got plenty of time, we've only been streaming like 30 minutes, I did want to watch the new Stuff Made Here video with you guys, if you're interested, because that is one of my favorite content creators. 1 second. So we'll maybe do that. I actually haven't seen it yet. I've been saving it so that I can watch it with you guys, chat. But first of all, any of y'all have any questions? I know there's only like 6 of you watching, but the 6 of you watching might have questions. I don't know. Saving my notes. Good. I'm glad it was clear. I mean, I don't know if I'm the best presenter yet, and I'm definitely not the best like note drawer. I'm actually pretty clearly a bad note drawer. But I'm hoping to improve, guys. And I'm hoping that I can keep things interesting, because that was one of my this is like one of my favorite things to talk about when I have to bring up like an engineering topic. There's a lot of cool stuff that I want to talk about, but this is like one of the top 10 things that comes to mind if someone's like, tell me about something in engineering, which no one has ever but the people in my mind when I'm having like when I'm having schizo conversations with myself, if they're like, tell me about something in engineering, this is the sort of stuff I love to talk about. And I see there was that one guy who had the weird spam message in Twitch chat, but I don't know how to ban them. Rest in peace. Wait. Anyway, I'll handle that later. I'll probably have to sort out mods at some point. But thanks for watching the lesson. Let's watch the Stuff Made Here video. Do. This one. Let's do window capture. We should put this here. And if we move front right, da-da-da-da. Guys, if you guys haven't seen this guy's videos, by the way, this guy's sick. This guy is sick. Wait 1 second. Okay.
Years ago, I made this
Whoa. Loud.
disc launching gauntlet. It was supposed to make me better at disc golf, but it just kind of ended up being dangerous. I couldn't let that stand, so I made this. It's basically a disc bazooka.
This thing is designed for accuracy. It has full control over the speed and spin of the disc,
And once we get sights on it, it should be able to snipe the basket.
and I'm hoping it can make me as good as a pro. It's also insanely powerful. It can shoot a disc faster than any human.
So we'll definitely be having some fun and shooting it at stuff. And yes, that's a sword.
I'm also going to show you the trials and tribulations of getting this thing working, and you're in for a treat because it was terrible.
Wait, but
Yes,
these discs, I don't know if you guys have played disc golf before. I mean, I've played disc golf a little bit. Actually, kind of like a decent amount. But, like, when you throw the disc, it has
That's
to
a
spin, right? So it's kind of weird that the sword can still cut it even though it's spinning.
I'm also going to show you the
Anyway.
trials and tribulations
Alright.
of getting this thing working, and you're in for a treat because it was terrible.
it really wanted to tear itself apart, and it refused to work in reality the way that theory said it should. So I had to rebuild and rebuild and rebuild. It has so many parts.
Now that I have this, I think there might be a simpler way to do it, but is there a cooler way? I don't know. This is pretty cool. If you're not familiar with disc golf, it's very similar to real golf, except instead of getting a golf ball into a hole, you're trying to get a frisbee into a basket. The second most important thing to know about disc golf is you never call it a frisbee, it's a disc. Frisbees are for babies, discs are for men. And at the end of the day, you're trying to get the
Discs are
disc
for men.
into the basket with the minimum number of throws.
The discs fly like little airplanes, so any variation in wind or how you launch them can make them go to completely different locations. In fact, I think it's physically impossible to consistently get hole-in-one. So my goal is for this to make me as good as a pro. Get to the basket in a couple of throws and then snipe it in. To do this, we need accuracy, which means launching discs with very controlled speed and spin. So with all this in mind, I went back to the drawing board and came up with a completely new design.
This is my kid's Hot Wheels set. It's also my general idea.
Specifically this little box down here. It has two wheels that rotate in opposite directions, and if we push a car into it, it launches it super fast.
This should work with a disc as well. This is a mini little fake disc golf disc. Watch what happens. If we shove it into the wheels. Oh, wow. No way.
Okay, chat. Just because I don't want you sitting here watching the video in silence, I'm also going to talk about what I'm thinking because I think it is also important to sort of like, go through the thoughts going through people's heads, especially when watching these videos because these videos are really insightful to see how like he engineers stuff, which is very good. But you should also see just like how having different points of view also helps. So what I'm thinking with this design, which I think is like a pretty good design in terms of getting the right speed and the right spin, what I'm wondering is there's an issue with like when you throw the disc, it's not just speed and spin. You also have to like throw it at the right angle, right? And I'm really worried that he's gonna put discs into his machine and they're just not gonna like come out at the right angle. They're gonna go, canted to the left or canted to the right, and that's gonna affect the aim. So that's what I'm worried about. But we'll see how it plays out.
Oh, so close. What's really cool is you can make it spin by making one of the wheels go faster than the other. But there is a problem.
There's a limit to how fast you can make a car or a disc go with this kind of setup. Let me show you what I mean. I've modified the Hot Wheel track to take this die grinder. Before, it was launching cars at maybe 10 miles an hour. On paper, this should give us closer to 40.
What do you think is gonna happen?
Pretty much the same speed. Here it is in slow motion. Do you see the problem? The launcher wheels are just slipping. The same thing happens when a car does a burnout. It doesn't matter how powerful your engine is, if you ain't got the grip, it's just gonna slip. But imagine if I took 10 of these launchers and put them in a row. The first one would get the car going fast, the second one faster, and on and on and on. It's basically a mechanical railgun. So if we did this and
Also, if you were in the chat when we talked about the railguns the other day, I swear I didn't watch this video before, so it's just coincidentally really nice that he's talking about similar stuff to what I've been talking about recently.
precisely controlled the velocity of all the wheels,
And yeah, also RIP Kids Toy Set. Rest in peace, kiddo. Baby stuff.
we could launch a disc with whatever speed and spin that we want. All right, let's get it made.
Oh, also, he's talking about how they're slipping. And if they're slipping, I don't think he's going to have as much control over the spin as he wants. Right? Because as much as you can theoretically control the spin by, like, changing one side to be faster than the other, if it's slipping, you're not going to have precise control. But, see it.
The hardest part of this project is going to be how do I grip the disc? I want to put a ton of force into it, but it's really hard to do that. So this is the simplest possible arrangement that I could build that will let me try different kinds of wheels gripping the disc. So we're going to just shoot the disc out, see what happens, go from there.
So do you think it's gonna work?
Here we
Hell
go.
no. Oh, actually not that bad.
I probably should have put a little bit more effort into it. This is a great example of how destructive vibrations can be. I'm gonna have to be really careful with this. Well, I'm glad I put the minimum effort into this thing because it stinks. Remember how I made a big deal about slip? Yeah. If you look closely, you'll see the disc bending when it goes between the wheels. This means I can't squeeze the disc any harder because it'll just bend more.
Every time I launch a disc, you can just smell burning rubber, burning plastic. So we're slipping. We really need a better way to grip these discs.
The direction I was going in is trying to grip the end of the disc with a V, kind of like a V-belt pulley. But thinking it through, it seemed really hard to do practically. But then I was thinking, well, if we put the wheels on top and bottom, that's kind of like a V wheel. With these, I can squeeze pretty much as hard as I want, so I can generate an enormous amount of friction.
We'd still put a set on each side of the disc so we can make it spin, but we don't actually need a tire on the bottom. We just need something slippery to squeeze against.
Before we can make the whole thing, I need to test it. I need to see how much grip we can get and see if it can actually work.
These rollers are the slippery surface we're going to push the disc against. I really like how the wheels are folded on top. They push the disc through, and by driving them different speeds, we can still make it spin.
So hopefully this will suck the disc in and spit it out like it tastes terrible. Let's see. Pretty clear the discs just aren't getting any spin. They're coming just straight out, which makes them very unstable.
We need the disc to spin so it acts like a gyroscope and resist turning over.
The wheels driving at different speeds should be able to spin the disc, but when the disc goes between two sets of wheels, it's touching 4 wheels at the same time, and it can't spin. It gets totally locked. You can see how much the tires are rubbing on the disc when this happens. I think what I need to do is spread these wheels out so that the disc isn't touching more than 2 wheels at any given time. So we're gonna redesign and remake a bunch of these parts to stretch it out like a limo and see if we can get that to work.
It's pretty much the same thing, just slightly different. Like twins.
There's enough space between the wheels for the disc to spin freely without jamming up.
Really not a lot to see for so much work, but hopefully it'll make all the difference. So let's find out. Okay, that is totally spinning. It's not perfectly stable, but it's way better, and we should get more spin with more stages. Based on the speeds I'm getting out of the test stand, I think I need 6 stages, but I'm gonna make 8 just to be safe. The wheels are really hard, so I'm gonna get them done first. This was harder to make than I expected. Vibration is a huge problem, so everything had to be machined extremely accurately. And even after all that effort, everything had to be carefully balanced. I spent a lot of time designing them to be easy to assemble because there's so many of them, which really saved my bacon because I ended up rebuilding these things so many times.
There's a really important detail that I've been glossing over, which is how much power we need out of the motors. And if you do the math, you actually need basically this motor inside of every single wheel. And this is the motor that I'm using. It is a little bit underpowered. Every motor will have a chunk of steel attached to it that looks like this. It's called a flywheel.
This will spin up with the motor and store a ton of energy.
Think of a car that's moving fast or a cannonball. Once it's going, to stop it, you have to take all that energy out. The neat thing about a flywheel is it can deliver an enormous amount of energy in a very short amount of time.
Kind of like a car hitting a
Just
wall.
build up a lot of momentum.
It's pretty amazing, but this little piece of steel can deliver as much power as this motor for a couple milliseconds, but that's all we need.
The rest of the machine is really similar to the previous ones. There's just a lot more of everything. I've actually had this idea for 2 years, but I was waiting until I got the water jet because I knew there was gonna be a lot of parts like this. Trying to machine all these in another way would be such a nightmare.
I mean, can you guys... I'm like 90% sure he's gonna have to remake a bunch of these parts because he's gonna have to redesign. Can you just like imagine how much time he's gonna spend rebuilding this stuff? It's so daunting to like make something really complex because basically 9 times out of 10 when you're making something it's gonna fail the first time, right? Probably gonna fail the second time and the third time. So you're gonna have to do like a ton of iteration, which you'll see a lot on this guy's videos. Because he does a lot of his videos just involve him iterating over and over and over, and you see like his whole design flow, which I think is one of the really cool things about watching this channel. But I feel bad for all the work he has to do.
Thankfully, a bunch of the parts can be 3D printed because there are so many parts. I designed the whole thing to be 3 modular sub-assemblies that combine together like a transformer to make a mighty launcher. This makes it a lot easier to assemble, and if I destroy something, it's a lot easier to repair. Do you remember those 5-foot subs from elementary school they'd bring to parties? That's basically what this is.
The biggest change is this thing. I don't love having a long thing hanging off the back of my disc launcher, but I think it's really important. We want the disc to come out very repeatably, which means we need to put the disc in very repeatably. You can imagine if it was angled up or down, it'll bounce through the system and come out differently. This is kind of like a mini launcher that cocks back and it holds the disc. And then when the computer's ready to fire, it'll release it and push it nice and straight with some momentum right into the launcher. The disc is held back with a trigger mechanism, which is really important for releasing the disc when everything is going exactly the right speed and getting consistency. It also has handles for picking it up like this. It's not that heavy.
It looks
And then
really
electrically,
heavy.
there's just basically 16 of everything, which was painful and expensive. And of course there's knee stop, because if things go wrong, you want to make them stop going wrong fast. Although there is a big problem. If I turn all the motors on at the same time, they're going to be pulling an enormous amount of current trying to spin up their flywheels, and it's going to be like 400 amps. Which will just melt everything, the battery will explode, it'll probably start a really foul smelling fire. So I have to do a little more complicated thing where I spin them up kind of one at a time, and that should limit the current to something more manageable. And then it also has a computer running Linux with a touch screen, which might seem overkill, but I'm planning to add a lot more smarts into this later. This is gonna give me an interface to make me way more accurate. The last thing we need is some software that'll calculate how these motors all need to spin to make the disc go the way that we want it to. And there's a lot of different strategies to do this.
The most obvious way would be to evenly split the acceleration between all the wheels, but this doesn't really work because physics. The amount of energy it takes to make something go from 0 to 30 miles per hour is the same to go from 85 to 90 miles per hour. You might remember the whole 1/2 mv squared thing.
Damn.
This is that.
Man.
Which counterintuitively means I need each stage to speed the disc up less and less. But this should actually evenly spread the load and give me the maximum amount of grip. And that's pretty much it. It's simultaneously not that bad, but also kind of complicated.
I think it should work, but there's
Alright, chat. Bets on if it works. I think it's not gonna work, in that it's not gonna be consistent enough. Because I think as this disc, like, it's getting squeezed between those wheels. I think it's probably deforming a little as it passes under the wheels, and it's probably gonna lose a lot of consistency from that. But who knows?
really only one way to find out.
So, here we go. Here we go. All aboard. Next stop, integration hell. When you put all the pieces together, it never works. I started off strong by blowing up half the motor drivers. But even worse, it's throwing discs even worse than me. I thought we fixed this.
I see a lot of problems.
The first is the disc doing this. It's not supposed
See, it's warping. I called it, guys.
to swim like a
It's as they squeeze it down, it's changing the shape of the disc.
whale. It looks like the disc's able to dip down between the rollers, and it pops up, and then develops a really bad oscillation.
Wait, I was a little wrong. I was a little off. But I think I was pretty close.
Basically a bucking bronco.
So I'm gonna try to put a guide right down the middle, and that'll hopefully stop it. So let's see.
Hey!
Oh yeah, that was way better.
The guide rails totally work, but there's another really big problem that I really don't want to solve. If you look at the disc closely, it's not really spinning. We try to shoot it far, it's just gonna flip over and slam into the ground. Ask me how I know. I think this is because I don't have good control over the speeds that the different motors go.
If they're going the wrong speed, the disc is just gonna do random stuff.
And this is happening because I'm using cheap motor controllers that have very bad speed control. If I tell
I think there's also a different issue here. I need Credo to show this. Hold on. Do. And this is me just sort of spitballing, shooting the shit, because he is actually probably a significantly better engineer than I am. But I think it's important to show you what's going through my head, just in case you're interested in, what other engineers might think. And you can actually talk with me. You can't talk with him. But I think if we have our disc like this, right? And we want it to spin at a consistent speed, what we really need is we need to know an exact speed at an exact point, like here, right? We need a very precise speed at a very precise point, right? So if you have the same speed, but your position is off, right? You're actually inducing that speed too close to the disc, too close to the center of the disc, then it's going to change the way that the disc spins, right? Because if it's spinning so fast that the edge goes, 10 feet per second, that is a different spin than if slightly in from the edge goes 10 feet per second. So what I think is actually very possibly an issue is that since his tires are so thick, he can't precisely control which part of the disc they're making contact with, right? You would think that it's here, but they could be making contact here or here, right? So I mean, I'm not him, and I definitely can't build the things he would build. But if I were working on this, I would use skinnier wheels for more precise control of where exactly we're applying that speed. And I think that would really help him, especially because what he said is he thought the issue was that he didn't have control over the speed, with those cheaper controllers. Okay. Back to the video.
Tell them all to go the same speed, they all go different speeds. We could either buy thousands of dollars worth of nice motor controllers, or we could do some really annoying engineering that I don't want to do.
All right, so I've been doing some engineering, and this is what I came up with.
What I'm going to try to do is measure how fast each wheel is rotating using one of these. This is called a Hall effect sensor, and it detects a magnetic field. So I have one set up right here, wired to this light, and if I bring a magnet near it, it will detect it and turn this light on. If we strategically place a magnet on each wheel and put a Hall effect sensor nearby it, we will see that magnet every time it spins by.
So now if the motor controller is going the wrong speed, we can quantify how wrong it is and compare it to the speed we want it to go and adjust the speed we're telling the motor controller to go until the speed it's actually doing matches what we want. We just have
This is a branch of engineering called control systems. It deals with error correction. So in this case, the error correction is like we have an input for the system, which is, electricity, and we have an output for the system, which is how fast it goes. And we need to be able to correct for the errors in how fast it's going by changing how much electricity we power it with. So these sensors let us know how off we are, and then if we need to go faster, we can drive more electricity. If we need to go slower, we can drive less electricity. And we can do that through control systems. That's actually my specialty as a professional engineer, so I think it's pretty cool, but just a little tangent.
to install and wire.
Oh, fuck! Sorry, I needed a transition.
This is happening because I'm using cheap motor controllers that have very bad speed control. If they're nice,
How fast each wheel is rotating using one of these. This is called a Hall effect sensor, and it detects a magnetic field. So I have one set up right here, wired to this light, and if I bring a magnet near it, it will detect it and turn this light on. If we strategically place a magnet on each wheel and put a Hall effect sensor nearby it, we will see that magnet every time it spins by.
So now if the motor controller is going the wrong speed, we can quantify how wrong it is and compare it to the speed we want it to go and adjust the speed we're telling the motor controller to go until the speed it's actually doing matches what we want. We just have to install and wire in 16 of these because there's 16 of everything. This is getting ridiculous.
So the Hall effect sensors work, but it still doesn't work because these motors. So watch what happens when I try to go 1,000 RPM, which is a very important RPM for me to be able to go. The motor drivers will not go below 2,500 RPM. So I think the right thing to do would be to get motor drivers that can go the speed that I want, but we're in pretty deep now, so I think it's time to go full sunk cost fallacy and just try to fix this in software.
So here's my plan. If I want a motor to be going slow when I fire, I can just turn it off before I fire and let it slow down. And rate when it hits the right speed,
Inaccurate.
boom, you're fired. But it's tricky with multiple motors going different speeds because they need different times to slow down. But I can have the computer calculate when to turn each motor off so they all reach the right speed at the same time. And when that happens, you're fired.
And when it works, it looks like this. You have all the motors going a precise speed to make the disc do what we want, and it's so cool. My wife is here to see what I've been up to. What do you think?
Looks big and complicated.
I thought this was gonna be easy.
You always think that.
I know, but I really thought it. It's like
You always think that.
it's a bunch of wheels. How hard could it be, There's nothing to it. Turns out there was something to it. You wanna press the buttons? You can see what this thing does.
Oh, thanks.
Are you sure?
Yeah.
You don't wanna fire it?
Nah.
How do you not want to
I
fire
love
it?
his wife.
I want to see what happens.
You gotta admit, pretty cool.
Yeah, you look totally normal. Take it on over to the old disc golf course. See what happens. You look like a vendor selling wheels instead of hot dogs at a game. Popcorn! Popcorn!
All right, so you ready to see the future? Here we go.
A lot of build-ups.
Get ready to take off.
That sounded good.
Didn't really look good. Hate to tell you.
I know.
I think his whole plan for, like, just letting the wheels slow down is, like, it's kind of scuffed because unless you're, like, very, very good at predicting the rate that they slow down, then the chances of you having them all hit the right speed at the perfect time, I think, are really low. But he made it work once. It's just consistency is such an issue.
Why? I thought I was done, but instead I got 2 weeks of pain.
This has been driving me insane. It was spinning before, now it's not, but I think I figured out what's going on.
It's almost the same thing as before where the disc would get locked between 4 wheels, but it can't physically touch 4 wheels. But I did increase the compression of the wheels on the disc, so now they're making first contact with the disc here instead of here, which is really good at stopping spin.
And I've tried so
Guys, I fucking called it. I fucking called it. Should have used thinner wheels. Oh well.
many things to try to mitigate this, but most of them didn't work. So we're not gonna go into all the details, but here's a little taste.
First I tried to fix it in software with about 10 different disc acceleration strategies. They didn't work. I tried so many things related to friction and wheels. I thought for sure this was gonna work, but it didn't.
I also thought for sure this was gonna work, but it didn't.
Well, rip me, cause the thinner wheels didn't work. But
Don't even ask. Do you know what really stinks? Having 16 of everything.
But I had an epiphany last night and I think I figured it out. So let's see. Finally.
did you just do one side?
You can tell it's working well when the discs drive across the net like a car. All of my fixes are based on the idea that it takes a lot less energy to get the disc spinning than moving fast laterally. So I'm splitting the boosters into 2 groups, spinny ones, not spinny ones. The first 4 stages don't attempt to spin the disc, they just accelerate it as fast as possible. And then the 5th stage starts it spinning. And the last 3 stages only have a wheel on the left.
And if you think about it, since it's pushing on the edge, this will push the disc forward, but it'll also spin it. And if you only have a wheel on the left side, it doesn't lock up. So all these things together let me get it going really fast with a ton of spin. So one downside with the front wheel arrangement is that we can only spin the disc one way, but I don't think it's a big deal. Something I want to fix, but for now, you can make the disc go as fast as you want, with as much spin as you want, as long as it's clockwise.
You could just add a second set on the right side and just have a mechanism to bring them up and down, so you can bring down the right side when he needs to spin it the other side way.
All right, it's time to touch grass, go
Holy
outside,
cow.
and find out what this thing can do.
Oh man. Now he has to hold it properly though. He has to hold it with so much precision. He's got the distance though.
This is far exceeding my expectations. It's possible because I set them low, but I'm just firing from the hip with no sights, and I'm getting the discs to land really close to each other. I can't imagine how good it would be with sights.
Ooh.
It's also really cool because it's showing how discs launched the same way can fly completely differently depending on their airfoil shape.
But don't forget, we can also change the speed and spin. This has a huge impact on where a disc flies and is going to be challenging for predicting where discs are going to go. All right, it's time for more speed.
So I think we may have found the speed limit. I ripped apart one of the wheels,
Oof.
and then I fixed it. Then we ripped another wheel off its rim, and then I fixed it. And we ripped another wheel off its rim. Around 90 miles per hour is where these wheels just say they can't take it anymore.
This is the sound
90
of the
miles
wheel
per
giving
hour,
up.
guys. Ooh.
I don't want to destroy
The
everything,
smoke.
so I'm going to stop while I'm ahead. But we got a few good shots in, and we're getting about 450 feet at 90 miles per hour. I think I should be able to do better than that, but there's a lot of things that can make you go short. So the problem I have is that I can't aim this thing because I don't know where the discs are going to go. They're like little airplanes, and depending on their speed and spin and airfoil shape, they fly in completely different ways.
So the first question is, if we shoot the same disc in the same way, does it go to the same place? So I built this really over-engineered test stand to prove it to myself. I did a lot of testing. As expected, it can't get a hole in one every time, but it's pretty good, and sometimes it can.
Guys, I know what I'm doing next time I go disc golfing. I'm building a fucking gun that shoots the discs, and I'm gonna take it out there with my friends, and while they're playing rookie disc golf, throwing with their arms, I'm gonna shoot my disc with a fucking gun.
And besides, if I can get even remotely close to the basket, I should be able to just snipe it in. We'll have to work on the speed, though.
I don't know how discs fly. I'm gonna have to make a thing to track the discs so I can get a lot of data. And then if I combine that with some software, which will show me on a map where it's gonna go, I can make some really nice sites that should let me play a really good game of disc golf. This video is already really long, so we're gonna do that in part 2. So if you're interested in that, make sure that you subscribe so you don't miss it. And we're not done yet though, because I have a thing that can shoot discs really fast. When you have something that can make stuff go really fast, you have to put stuff in front of it. Like, I have to know what happens if I put this machete in front of a disc coming out of this. We're gonna find out. I just got up. It's way too early to be filming, but I wanted to show you what I do every day. I think this is one of my superpowers, and it could be yours too. So let me show you. That's good. No matter how busy I get, I spend at least 30 minutes a day learning something new. This is how I've picked up a lot of my skills. And one of the tools that I use for this is called Brilliant. I use it all the time. It works really well. And I'm really happy to have it for this video sponsor. So let me show you how it works. They have a range of big technical topics: programming, AI, math, data science, and they're broken down into literally thousands of lessons. And each of these is just the right size to do maybe 1 or 2 a day. And today I'm doing a lesson on multivariate data modeling. I'm not very good at it. I'm getting better. So let's get into it. So it just taught me some theory, and now it's having me do some examples. So you learn and then you do, which is just the best way to learn. It's part of the reason I love making stuff. I love doing. The examples are also interactive, which really helps you build intuition for complex stuff.
After working through a few more concepts, I'm done.
I would love to be
I now know
sponsored
a little bit more,
by Brilliant Pimpin'.
And I'm telling
That
you,
would be
this is
so
my
cool.
superpower. Spend a bit of time
Also the Adventure Time shirt. I just wanted to point it out.
learning every day. You will be shocked
Shane's so
how much
cool.
you pick up in a year. So if you're interested in leveling up your problem-solving abilities, check out Brilliant. You can try it for free for 30 days. Just go to brilliant.org/stuffmadehere. You can also click the link in the description, and you'll also get 20% off an annual premium subscription. And that's it. Thank you, Brilliant, for sponsoring this video, and thank you for taking the time to check it out.
All right, let's blast some stuff with some discs. It kind of goes.
Who needs a machete like this? Why do you have this, Shane? The only reason you would want to have this is to do cool stuff with it, like this video, which I mean I admit is cool, but like that, I feel like it's impractical to have this fucking nasty murder weapon.
Without saying, but don't try this at home.
And this is exciting enough that I invited my wife over for the festivities. Are you as excited as I am?
Probably not, but I am excited.
No one knows what's gonna happen. What do you think is gonna happen?
I think the frisbee's gonna.
It's called a disc.
It's not gonna go all the way through or something.
I think it's gonna be the most amazing thing you ever saw. After me. With this one, you need to go hide outside or something because you don't want an errant disc to the belly. I'm willing to take an errant disc to the belly. I'll flex when I fire.
Dog, just put like a shield up. Come on.
And we're gonna do it in
Acrylic shielding.
3, 2, 1.
How you guys think it's gonna cut through? I think it's gonna cut like 2/3 of the way through and then bounce off. Or like just get caught on the blade. Oh my god! Look at the jiggle on this thing. That's some jiggle physics. Holy.
That's got to go on the wall for sure.
I also am like surprised that the cut is so like straight through it because the discs. I mean, I guess the discs aren't spinning like that fast, but I thought it would like if it cut, it would have like a really like curvy looking cut because the discs are spinning.
That's got to go on the wall for sure.
That is cool. I wasn't expecting that.
Very cool, very cool. Are you impressed with me?
Yes. Always.
Are you impressed with this?
Mostly.
It sliced a disc in half. I think this could legitimately make me really good at disc golf if you count using a bazooka playing disc golf.
Yeah, it's not a discreet way to cheat.
Yeah, I don't know how you'd hide this under a trench coat or
That's
something.
exactly what I was thinking.
Anyway.
Disc launcher? Or...
All right, we're done.
Hell yeah, chat! I love this guy. If you guys aren't subscribed to this guy, you should subscribe to Stuff Made Here. All his videos are top tier stuff. This is why I became an engineer, guys. I want to do shit like this. Although I never will because it's so daunting. It's so daunting to start a project so complex. And he must be some sort of genius. Because I could never. But he's a great inspiration. Oh man. Yeah. If you haven't subscribed to Stuff Made Here, check him out. He's super cool. Alright. I'm so glad I got to watch that with y'all. I also feel like it was really coincidentally like sort of tangentially involved with stuff that I've talked about recently. So, especially like all the slip issues. Ugh. The chance that it's on the day that we talk about cars and slip. Good luck to me. Okay, how are we for time? Streamed for a little less than an hour and a half. But I think I'm gonna call it there. So, thanks for watching, guys. I'm super happy to still have viewers. I hope my lesson wasn't too scuffed. I know I'm still pretty scuffed, but I'm super happy to have some people to stream to, and to teach all this stuff too. I hope you guys are like enjoying the teaching. I know it's sort of nerdy, and I'm a bit of a nerd, but yeah. All right. Cool. I will call it there then. Next stream will be Friday. That'll be just a chill stream. We're just gonna kick back and play some games. I've had Jedi Fallen Order for like 2 years now, and I still haven't played it, and I really want to play it, so we're probably gonna try and play that. So yeah. Thanks for watching, and I hope I see you guys again. I'll be streaming Friday. at 9 p.m. Pacific. If you can't make it, that's fine too. But we'll be kicking it. Alright. Thanks, everyone. Have a good night.